people might find that confusing. So that's just a mapping between letters and what I write. And also there is a bunch of, if you want to look like further into some of what I'm going to talk about, these are some references. So I'm not going to talk about anything that is my own research, though I use those techniques. But this is actually like a lot of those are at least as old as I am. So this is from computer science and has introduced those notions. There's some asterisk on the first because I don't think it's actually ever been published. It's just some like presentation that I couldn't find any written record for. So yeah, today it's going to be what is deterministic amplification. And I'm going to start trying to by trying to motivate the question. I'm not going to try to give too many proofs, though maybe a little bit, just like what that is about. But yeah, so what is deterministic amplification? And so the first question is going to be, have you heard of primality tests? You know, like I give you a number and I ask you, is it a prime number? So we know how to do that. I think we've known for a long, long time now, that is, at least the Greeks. But now the question is, how do I do that efficiently? So again, I give you a number and I ask you, is it prime or not? I'm not asking you to give me the decomposition like factors, but is it a prime number or not? And so we know how to do that in a randomized fashion. We have very good randomized algorithms for that, including I think the most prominent is called the Miller-Raving test, which sure I can give the details, but basically it picks some random stuff, it does a bunch of tests, and if that passes all of them, then it says yes, it's prime. Otherwise, it doesn't. Like it says no. And of course, there's a probability of error, so you repeat that a bunch of times, and then you end up having a probability of detecting when something is not prime. So here, like coming from a computer science point of view, we have an input which is the number I want to check. So let's call that n. And so the size of the input is going to be log n. Should be at least consistent with what I did. So also that's binary log. So we want to be efficient on that, which means running in time polynomial, etc. So the Miller-Raving test, ignoring some additional stuff, runs in that time. I think that's the most efficient kind of way you can do it. I'm hiding some stuff, like maybe like I can put that glorious thing here. I won't, just to say that there's some extra stuff in there. So that's ultra efficient. That's basically almost like that would be almost linear in the size of the input. And that gives you the right answer with some probability, which is 1/4 of error. So like 3/4 probability of being correct. So that's the actual formal guarantee is, so if n is prime, and if n is not prime, I think that's the only two options, then we have different probabilities of being correct. And so here it's going to be, if it is prime, then it is correct with probability 1. And if it's not prime, I think that's what it gives, something like this. So again, like, this is roughly what that gives. A fancy way of saying that, I'm going to give some definitions, but that's saying that primality is in co-RP. I'm going to give the definition later, but so we get this, and so we're very happy with that. It's very fast and so on. Now, can I do that deterministically? Does anybody know the answer or not? Can I actually like check primality deterministically? We also got to check here. There's something in the chat, but I don't know if it's okay. So it was a big question, and the answer is yes, we know how to do that deterministically. There's a paper from 2006 by Agrawal, Kaya, and Saxena. The paper is aptly named Primes in P. And that was a major breakthrough, by the way. Like don't know the algorithm. I think I could read the paper, but I don't really want to. I couldn't try present it in 1 hour. So this is great. So this is saying primes is in something called co-RP. So we know that.
This is probably a horrible polynomial.
Yeah, so this is really fast. That's almost linear. Again, like I'm hiding something here. They showed, so that's AKA 06. They showed something which was, so there's, I'm also ignoring the same tilde on this, but they showed something like this. So log n, but to the 12. That was the conference version. Then like, there was the journal version that showed something like log to the 7.5. So still, you know, like the size of the input to the 7.5, which is not great. And then that was improved by 2 other people, Lenstra and Pomeranz, to log to the 6. And I think, I'm not sure, but I think like modulo some conjecture in number theory, that could possibly be 3.5. But I mean, this is still, think of log n as big because that's kind of what we want. We want a number that is like 1,000 digits or something. That's still pretty large. So it's not clear whether we can do things actually efficiently, like in the Miller-Raving tests. But at least we know that it's also in. So here I'm not going to talk about how to actually do things really deterministically. Deterministic amplification is more, I've got something like this, but I want to make it better in some way. So we're not going to get an actual deterministic algorithm. We're going to just try to minimize the amount of randomness we need to do that. Because, I mean, 3/4 is not great. I would like to get something much better. And as we will see, a naive way to do that is just to repeat the same thing again and again and again and take like a majority vote or whatever. You know, if anything at some point says no, not a prime, then I know it's not a prime. But if I do that, that's going to increase my running time. That's going to increase the number, like the amount of randomness I need, and that's actually sometimes a limiting factor. So deterministic amplification is not about how to actually get something fully deterministic that would be de-randomization. It's more about, I want to amplify that 3/4 or whatever to like 0.99 without paying too much.
It's like taking red tests.
Sorry?
It's like taking rapid antigen tests.
Yeah, though like it's doing it with expanders at some point, so I guess. But yeah, so now if you're not convinced, that's an important question. A small anecdote is random bits are actually like very hard to find in nature. So I like that at some point I visited a place where there are literally lava lamps. I don't know if it's an urban legend what they're for or not, but there's a wall with lava lamps and a camera looking at them, and apparently the purpose is to actually extract randomness from the patterns, because at least those we don't know how to predict. And that's in San Francisco, and that's used for some like internet protocol of some sort. So I'm not sure whether that's just, you know, an urban legend and they keep the lava lamps because that looks good, but it's really hard to get certified randomness. That thing can actually be expensive, and getting something that is truly uniformly random to use in your algorithms might be a problem in practice. So I'm gonna give the definitions of 2 complexity classes, because why not? RP and BPP, and then we can just forget about that for the rest. But so I also think that computer scientists are very bad at naming things. So this is randomized polynomial time, and this is bounded probabilistic polynomial time. But I don't think, and co-RP is the same thing, but you replace the answers, like you swap the answers. Anyways, the idea of this one is I'm a randomized algorithm, but I will only make one kind of error. So in that case, I've got an algorithm that takes some randomness. So that's the randomness of the algorithm. And given some input x, the probability that that's going to be yes or no. And I want to check what that thing is. So the probability that it says yes should be at least, say, 1/2 if x is like a yes, and 0 if x is a no. So again, I only make one kind of errors. I always find that very confusing. So yeah, so basically if that says yes, you know for sure what the answer is. If that says no, you're not quite sure. If you look at the thing the other way around. So that's often called one-sided error. If you're familiar with like computational complexity, that's kind of the randomized equivalent of NP, because there's like when it says yes, you can use the thing as a witness. But anyways, that's called RP. And as I said, co-RP, you just read like it's the opposite. So primes wasn't co-RP. If those are like confusing, don't worry. I was very confused about those as well when I made my notes. I had to double check. So think of that as one-sided error. I only make a mistake in one of the two cases. And then we've got BPP, the other thing that is just saying, let's say 2/3 and 1/3. So BPP is the one I can make a mistake in both cases as long as there is a gap. My probability of making a mistake is at most 1/3. So those are the two main things here. And of course, there's something else we want. We want A to be efficient. Meaning runs in polynomial time in the polynomial size of the input. Yeah. So once you have that, you have defined those two classes of decision verbs. And now again, here's the thing: I define that with 1/3 and 2/3, and like you could be, well, what are those numbers? If I replace 2/3 by anything that is strictly greater than 1/2, a constant, and this by anything that is strictly less than 1/2, I don't change those things. That's completely arbitrary. And same thing for this one, I can replace 1/2 by like 1/pi if I want. That doesn't change anything. As far, yeah.
Oh, sorry. I'm just wondering, efficient if this runs in expected polynomial time, or
No, those are it has to run with probability 1 in that time and give an answer. So now the question is that, well, this is 1/2, this is 2/3. People are rarely happy with something that is only correct with probability 2/3. So now how do I make that correct with probability 99%, or even like 1 minus delta for delta going to 0? So so I'm just going to call the runtime, the runtime is going to be T. And here I'm using some randomness, but since in this talk I actually care about the randomness, I'm just going to look at the number of random bits I'm going to use is R. So those are two things that I will have to keep track of. But in all that, I start with like, I'm considering some problem, and I assume I've got some algorithm A that uses that many bits of randomness. And runs in time. And I'm not going to try to be clever in the sense of, I'm not going to try to say, oh, maybe I can look at what A is doing under the hood and try to optimize that. No, I'm given that algorithm. All I want is to use it as a black box to get something better. So I claim that there is a very natural way to just get from, I don't know, pick your favorite poison, like from 2/3 to 99%, and from 1/3 to 1%. So what? Yeah.
What's
So here, it's a randomized algorithm, right? So actually, I could rephrase that as saying that X is the input, and it also takes a random string here. And so the probability to be correct depends on the random string. So the algorithm tosses some coins and looks at the result. And implicitly, we assume that those things are perfectly uniform, or they're nice. So what would be a natural way to go from 2/3 to 99% if I don't care about like blowing up the time and resources I'm using?
When you keep doing it, right? Because
I can just repeat that on independent random bits. And well, let's look at this one. If I ever see one of them saying yes, sure, that has to be a yes. And I can repeat that k times. So let's focus on RP here. Okay. So I can repeat that k times.
that goes equals to get some incidental.
Okay, so I should use the black one preferably, I think. Otherwise, I'm gonna have a full workout. So if I repeat k times, well, let's look at RP. What would I do? I just say yes if I ever see one that says yes. If they're all no, I say no. So then the probability, still 0 in one case, because that's never going to happen, the probability of error in one case. But the other one is going to decrease as 1/2 to the k. So that's good. If I want to achieve probability of error delta, I get like k is equal to log 1/delta, and I'm happy, except that now the time I spend becomes k times t, and the number of bits I use becomes k times r. So again, to achieve, I don't know if I'm going to be consistent, but to achieve delta, probability of error delta, I would need to take k is equal to log 1/delta. So in that case, that becomes.
You mean that kind of checks attention? That means that the chance of you getting a wrong answer is now 1/2.
Yeah, the probability of error. Yeah. Sorry, delta is going to be my probability of error. Yeah. But as a result, I spend more time and more randomness. So that's not necessarily what I want to do. So that's for this one. And for the other one, the EPP one, I can't just say like if I ever see a yes, I answer yes, because I can make mistakes in both cases. So there's something similar I can do. I can just count the number of times I've seen yes and look like threshold it, basically take the majority vote. And if I do that, you can also show it's not going to be the same expression, but like you can use some Raving bound, concentration bound to say that, well, given the fact that in one case I see yes with probability at most 1/3 and the other one at least 2/3, if I take roughly log 1/delta, but with some constant factor in front, and I take the majority vote, I will achieve the same probability of error. So that's still good. But I will have exactly the same issue, then my running time and my amount of randomness will blow up. So is there a way for me to do that without paying this, basically, to achieve the same thing without paying those things? Either, so again, the motivation is randomness is very expensive. I just don't have true randomness. Or my certified randomness can be very expensive because someone can tamper with the random seed I'm using. Or just, in distributed applications, you put like a bunch of people that have agreed in advance on some common random seed, and once you use it, you don't get it back. So can I do something like this without paying that factor k, but still getting at least some decrease? And I'm going to show like a couple options, but the first one is not the, so what I would like ideally is not pay anything, right? I would like to get the same exponentially decreasing probability of error, but like without the case. Yeah. I'm not going to give exactly that, but the first thing I could do is, well, yeah, I'm saying I'm using independent, like I run independently all those things. So all the k things are on independent randomness. Maybe I don't need fully independent randomness. Maybe just that's way too much. And one first idea would be, if I'm willing to lose that exponential but just get something decreasing, I could use something much weaker. So I could say that I'm just going to use instead of OFDing or Chernoff, those things that give a exponentially decreasing probability of error, I could just use Chebyshev's inequality. Why is that good? Well, Chebyshev's inequality, or it could be a bit more refined and use like moments inequality like that, is just saying that if the expectation is something, so in one case is the error is at least at most 1/3, yes is at most 1/3 probability, and in the other case at least 2/3. So the expectation is there's a separation between the two. If I can bound the variance of that thing, then I can use Chebyshev's inequality to say, oh, I run a bunch of things, I look at the majority, I can bound that via Chebyshev, and I get something that decreases as well. It's not going to decrease as 1/2 to the k, it's going to decrease as 1/k. So that's much worse. But now again, something quite good is Chebyshev's inequality. It's just looking at the variance. The variance is just, well, it's the square of, like, if I take the sum and I square it, that's going to be basically the variance. That means I don't need full independence. I just need things to be pairwise independent. I need my runs to be pairwise independent. So I will run the algorithm still k times. K is going to be 1/delta instead of log 1/delta, but I just need every two of those things to be independent of those randomness to achieve this. So again, instead of running all that on independent chunks of randomness, so like L1, I think I'm using a big letter, RK, and those things need to be fully independent, and I get this. I can just say that I'm going to go with something much weaker. I only ask any pair of them, if I look at them individually, to be independent. And then I can achieve something that decreases as 1/k, but using pairwise independence. And one good thing about pairwise independence is we know to build that in a much cheaper way. There's a standard thing which is just take a uniformly random variable, only one. So I can just pick something that is x uniform. So I pick a prime that's going to be roughly k. I pick something that's uniform on, so let's assume k is prime, on zk. And I compute all the things of the form Ri, and I'm going to define that as, two things, x and y, x plus I times y modulo k. For I, basically between 1 and k minus 1, but let's just say k. So that gives me k of those things, but I only start with 2 random variables. So that's using a lot less randomness. Those things are not independent. Of course, they're not. If I give you all of them, they are not independent, but they're pairwise independent. Like the proof is like half a page, and those things are pairwise independent. And again, that's enough, because if you want to use Chebyshev's inequality, you only need that to bound the variance. So that's one way. And what does that give me? So again, that's what we started with the naive approach. Here, I just basically get a 2. Because I just need 2 things to start with. I think that, yeah, if you look at the parameters, you will end up with a 2 instead of that. So I still run in much more time. I use much less randomness, only a factor 2, but now if I want to achieve the same 1/2 to the k, well, that doesn't decrease that much. So actually, like, the running time is going to be exponentially worse in that way. So it's not perfect, but if you just care about randomness, that's one way. So that seems good. But again, I still use a bit more randomness, and I still don't fully achieve what I want to do. And that's where there is this. So that was in this one from Cohen and Victor. That was from Shaw and Gondrak from 89. But they just said, like, we could just use this 2-point sampling idea and get things a bit better.
Can I just ask, what would, in the prime example, what would bounding the variance look like practically?
Oh, so yeah, I've got the expression somewhere. So,
oh, yeah, repeat the question.
Oh yeah, sorry. So the question is, what would bounding the variance would look like here exactly? So this one should work. So again, to bound, what I want to do is to bound the variance of this to be able to distinguish between the two cases. I make a mistake and in one case, and I make a mistake in the other. So I'm just going to repeat. So the thing I want to bound is I'm going to define my random variable as S. So I just look at. So I run the thing k times. I run the algorithm k times, and I say like, what is the fraction of things that give the right answer? So I don't know exactly what that is, but A of like AI, the I run on X is correct. So that's the random variable I want to analyze. I know that in one case, so let's look again at this one. In one case, this is going to be 1. And in the other case, so case 1, I have this, case 2. So let's say not correct, let's say answers yes. That's going to be easier. So I don't, maybe I've mixed the two, but and in the other one, I say I know it's less than 1/2. And so I want to bound the variance of S so that it has to be less than some constant. What I want is to be able to distinguish between those two cases. And the variance of S is going to look like something less than if. So I know that here I know I've got that bound 1/2. So I think the bound I would get is 1 minus 1/2 over k. More generally, if instead of 1/2 I got some like delta 0 or whatever, I would get delta 0, 1 minus delta 0. And so to be able to distinguish between the two cases, I would like the probability will decrease as 1 over k, and I have to set that less than the final thing I want to do. So like the probability in question would look like something like this if I use Chebyshev's inequality. I guess that would be the gap between the two. And so I need that thing to be less than my target delta of error. So I would get like k needs to be 1 over delta for that. We can do something a bit better if instead of pairwise independence, we can do something more like 17-wise independent. In which case there's an equivalent of Chebyshev that uses higher moments, and so you've got that trade-off you can achieve. I'm not going to talk about that right now, but there are generalizations of this particular technique. I want to talk about another one that does something absolutely different. And to do that, I need to define what an expanded graph is, and I'm not actually going to define it formally. But there's an approach that allows me to get almost what I would like to define what ideally paying very little.
So you talked about the trade-off between running time and randomness.
Yeah.
Should we think of randomness as being somehow equivalent to some additional running time, or could you compare the two of those things somehow?
So I don't think that really depends. I think of that as a resource. Basically, you're given like a time resource and a randomness resource, right? Because for example, if your algorithms are parallelized, you don't care at all about the running. I mean, the running time is just all in parallel. You can run those things in parallel. But maybe then, like the randomness is really the thing that you can't afford to get too much of because you would have.
Right.
So
is that like maybe like a data collection thing or something like that? Is that what you mean? Or
sorry.
Would you think about the randomness as somehow being something you can't necessarily generate more of?
Yeah. Yeah. Right. So for me, like the typical application is that a bunch of computers or like cell phones or like probes that I've sent and have like, in advance a random seed that they share. Yeah. And well, once they've used all of that, there's no more we can get. But again, like another thing would be just, oh, maybe this thing is actually expensive. So I've seen, I'm not a systems person, but I know that, for example, like the Linux kernel cannot generate that much good quality randomness at a time. So once you've used it all, you need to wait for it to be replenished. So I'm just not going to define exactly what an expander graph is, but like it's something that looks random. Sorry, like, I know this is very lame in terms of the definition. It's basically like I've got a graph, and like it expands like a random graph would do. So I have basically the same kind of the same kind of connectivity I would expect from a random graph. I'm not going to be more formal than that, first of all, because I'm sure there are people that are way better at explaining that than I am. But I'm just going to write one lemma to try to capture what this means and try to explain other use. So, for example, I've got a graph on n vertices, and I'm going to assume it's d-regular, meaning each vertex has the same degree as d neighbors. And there's something called spectral expansion, which is if you look at the adjacency matrix of that graph and you look at the eigenvalues of the adjacency matrix, then you look at the gap between the first one and the second one. And you want, So lambda is the spectral expansion, which is related to the adjacency, the eigenvalues of the adjacency matrix of that gap, of that graph. And I'm just going to use that as like, those are magic graphs that just look random. If you're interested, this is literally called expander graphs and their applications. It's a survey by Uri Linian and Adili Besson that explains where to find them, not quite the most recent, what we can hope for, first that they exist and how they can be used. But I'm just going to use that.
The audience that's useful to say, like, take the K graph of a simple group, or take the K graph of a family of simple groups.
So usually I just think of literally like, why do those things exist? There's a probabilistic argument that says if you pick a graph and for them, then it will have the nice properties you want. But yeah, so actually that's the last thing here. At the end of the day, we want to have one of those things and be able to access it very efficiently. So there are some extra like computational requirements. And if you're interested, there's a sequence of papers lately that show that you can get expanders that have almost the optimal bound in terms of lambda. So like there's something you want, like there's a bound like how small that thing can be. And they achieve it up to some constant, and you can actually build that graph, not just build the graph, but actually access the adjacency matrix of the graph very efficiently. So given any vertex, I can tell you what the neighbors are, and I can do that very efficiently, which is useful for applications because, as you will see, I will want a graph that's like exponentially sized. So if I want to actually do anything with that, I need to find a way to access it efficiently.
So in Josh's comment about randomness as a resource, you can generate expanded graphs randomly, but you don't want to because
I don't want to because otherwise that loses the whole point, right? So yeah,
so this is like an implicitly given graph.
Yeah, I want to be able to say like, given parameters n and d, I have a way to just like create that graph and query it very efficiently. Now, like the random part is just like, do those things exist with the set of parameters I want? And I can just say like, yeah, they exist because, if I take a random graph with some positive probability, there's going to be one like this. But that's not what I want to do. So this is just like, I assume I'm given one of those things. I assume I can query it like ultra efficiently, and then I'm good. But yeah, definitely I don't want. The last part is, can I actually get one efficiently? And that's where there is some work that I think a line of work that achieved almost the optimal bound, and I think now like we have the actual optimal bound up to some constant to get the lambda we want. So, I'm not sure I have the reference question, but yeah, we can achieve something like lambda is less than 1/√d or something like that, up to some constant. I don't think we have pinpointed. I don't think they have pinpointed the constant exactly. But yeah, I don't want to generate those things randomly. I just wanted to say like those things exist because there's some. Like, either you look at the papers that actually build them, or you just like me, you just like, well, there is an argument, there is an existential argument that says they exist, and I'm just going to assume I'm ended one of those, and then that's good for me. So there is
one more question, just so that we're on the same page. Then, so I have the kind of provenience from eigenvector or eigenvalue, and by spectral you mean that eigenvalue minus the next modulus.
So yeah, so lambda of G. So I've got the eigenvalues that I think I ordered that as being. So I'm the normalized adjacency matrix. So I've got those eigenvalues, which I think are like this. And the definition I have in mind is the maximum of lambda 2 and lambda n. So I want that thing to be as small as possible. And the reason is, so that's just the expander mixing lemma. Oh no, I'm using the red one, it's going to be out. That says if I've got something like this, then, so it's deregular and that's spectral gap of that form, then for every two sets of vertices, so I take two sets of vertices, and there's going to be some number of edges between them. So S and T, and I'm just going to call that E of ST. Then E of ST. So I look at the number of things between them, and I normalize by the fraction of things I could have had in total. So I divide by d times n because it's deregular and I've got n things, and it's going to be equal to. Ideally, what I would like is this. I'm not going to get this, but ideally, I would like this. I would like the number of edges, like the fraction of edges between those things, to be roughly related to the size of the two sets. I can't get that exactly, but I can get something that is nearly as good, which is that lambda appears here. So that's why I want it as small as possible, divided by I don't know if that's visible from the camera, but think of that as the standard deviation kind of thing. So if lambda was 0, then that would be amazing. But I want lambda as small as possible. And we know that the best we can hope for is lambda decreasing roughly as 1/√, of the degree. So the question is, can we achieve that? I think, yeah.
So it's S times T divided by n squared. Is that what's the equation for why you want?
Oh,
You want to ship out of it. You want it to be very hard to chop. Yes, that's the review.
Oh, right. Oh, that's the maximum number.
yeah. Yeah, you can't. So,
And lambda equals lambda G.
yeah, sorry. Yeah. So once I have that thing, so let's assume, and we know that lambda, the best we can hope for is lambda G to be roughly, I'm gonna ignore constants, like something like 1 over square root d. So that, again, that probabilistic construction which would get you that. We know we can't do better, and I think we know how to achieve that also efficiently, or to build those things. I don't know the specifics, there's probably some restriction, like D needs to be like a power of something, modulo something else. But we know how to do that. And at that point, it's not clear at all why this is helpful for anything I've talked about. But now let's just say that I'm going to set a very specific set of parameters. Maybe. I'm going to say, so I've got an algorithm that uses R bits of randomness. So I know that I can do anything. I can pick a number between 1 and 2 to the R at random. Right? If I've got that many bits, I can just use that to pick a number. So I'm going to take n to be 2 to the R. So my graph is just going to be a bunch of nodes. And with that amount of randomness, I can pick one at random, uniformly at random. And I know that all of those things are, it's a D-regular graph, so each of them has D neighbors. It's a little set of D neighbors. So what I can do is I use my bits of randomness to pick one vertex, and then I look at all the D neighbors, and I look at them, and well, they're nodes, but they're also numbers, right? I can label them. So I can actually look at that as each of them a random seed. So I can look at those as like D random seeds. And I can run my algorithm on those numbers using that as randomness. And somehow doing that, because it's because of like, I don't know if I will have time to do the proof, or like if there is any desire to do the proof, but if I do something like this, of course, I'm still on a, I'm going to use R bits of randomness because that's what I get, that's what I use to pick that node. I'm going to use, so I call that D. So like, sorry, kind of messed up my notation. But the running time is going to be D times T because I run the algorithm on like R1, etc., etc. I can do the same either for like RP. I would just check if one of them says yes. For BPP, I would take the majority, but I still can do that. And now I will achieve, you can show that doing that, you achieve probability of error, which is roughly 1 over D. So that doesn't sound maybe that impressive compared to the one like with the 2 point something thing. What I did to achieve the same guarantee is I don't have a factor 2 here. So using exactly the same amount of randomness, I can decrease the probability of error like with the Chebyshev based thing, but I use 0 extra bits of randomness. So it's in the case where like, you really can't afford anything. And of course, it's a much more involved thing because now I've got to be able to build that efficiently. As I said, this is a big graph, right? So I can't afford to even build it. I need to be able to say like, I pick a vertex uniformly at random, and I want all the neighbors, and I want to be able to do that efficiently. Otherwise, the running time is going to be dominated by like the time to construct the graph and all that. So it's a much more complicated approach that saves me a factor 2 in the number of random bits. So maybe at that point that doesn't sound that impressive. So there's something else we can do with the expanders, and it's just like, well, I pick a random thing here. So let's say I'm here. Instead of looking at all the neighbors, I can just take a random walk. So instead of just looking at all the neighbors, I'm just gonna take a random walk. So each time I want to take a step, I have to pick a new neighbors, right? Each time I've got the choice between two neighbors. So each time I've got to pay log D random bits every time I want to do one of those steps. But let's do this. So I do a random walk of size k. So I start at V0, then I go to V1, V2, etc. vk. And I'm gonna again look at those vi as corresponding to some random string, because again, there's a direct correspondence between those things. And I'm gonna run again the algorithm on all of those things. So I'm still gonna pay, okay, this time I'll be consistent. I'm still gonna pay k times t here because I ran the algorithm on each of those things. And again, I will do the same. Either I take the majority of outputs or just like, they need to all be no in order for me to say no. But now the number of bits I'm going to use is going to be this plus k log d. But the probability of error I achieve, okay, it's not exactly the same exponent as before, but it's still going to be like 1/2 to the, I think it's going to be k/2 or k-1/2. So let's just put this here. So now this decreases exponentially again. And that's good. So in particular, I can just set, I just need the degree to be a constant. I don't need as before. So with the previous approach, I needed the degree of my exponent graph to actually be something that's scaled. Now I just, any sufficiently big constant, there's like some dependence between the d needs to be a sufficiently large constant with respect to 1/2 or 2/3 or something, but a constant will do. And I achieve exponentially decreasing error, paying, this time I use some extra randomness, but additive. So I don't actually use the same, multiplicative kind of thing. So I think that has a name that's probably like the expander, like Chernoff-bound or something. But that allows me to only pay an extra small amount to get something like this. So
here you're using that, like, if you go on this walk, some property of the expander means that all of these are now fully independent again.
So yeah, it's using some kind of things like that. It's almost as good as if I add actual independence. It's not quite as good, so that's why like the exponent is not as good as that, but it's pretty good. I don't know if the exact exponent is probably known. I don't know it, but that means that you would get the same kind of. You would take k to be log, like big O of log 1/delta to achieve error of delta.
The time.
Yeah, so I'm done.
Why is it k log d?
Oh, what is k log d? Oh, because every time I want to take a new step, I'm in a d-regular expander. So I have to pick a neighbor uniformly at random. So that takes me log d random bits. And I do that k times just because I do a random walk of k steps. So, but again, then I just need log d to be like d to be a constant, so log d to be a constant. And if you're willing to ignore constants, it's r plus big O of k. So yeah, that's pretty much all. I don't know if there are. I have no idea if there is any question on the chat, but if you're interested, I can recommend you really to this, which contains most of what I've talked about. There's some annoying little thing that they get the definition of RP wrong, which I noticed this morning, so that threw me into like some kind of deep rabbit hole of doubt. But it contains not only what I talked about, it also contains like other applications of expander graphs, or to build them, at least when they are at the time. If you're interested, there are a lot of applications of those things in theoretical computer science. And I don't have the exact reference, but I know that Ryan O'Donnell and collaborators and students also got how to achieve the best possible regime of parameters up to constants in terms of those spectral gaps and be able to access them very quickly. And that's pretty recent. That's like just pre-COVID. So not so long ago, or an eternity ago, depending on how you look at it. So yeah, if you're interested, I can point you to those things. But again, just the summary is there's a naive approach that is just repeat a bunch of times. If you care about randomness or running time, there is a lot more you can do, although it gets more involved.
Thank you.